Hey guys, Smith here. I'll make sure that at the end of this video you like and subscribe. Remember Newton's fourth law. If you like the video, smash that like button. But what we're looking at is how all of these things come together for our last look at Newton's laws. So the one that we've talked about the least is the idea of Newton's third law of motion. Newton's third law of motion is the idea that if you have any two objects in contact, any two objects interacting with one another, there's an interaction pair. So when we draw a free body diagram, we usually start with the weight, the earth pulling on the object down. The interaction pair to that isn't the normal force or tension or anything like that, because those are also acting on the object. The interaction pair is the earth pulls on the object, so the object pulls back on the earth. Now we don't notice that because the earth has so much more mass than the object, so there isn't any measurable acceleration. So that is the interaction pair there. The other option is if you're sitting on the couch, the earth is pulling down on you, you're pulling up on the earth, but because the earth is pulling down on you, your body is trying to accelerate downwards. Now that means your body then pushes into the couch. So if you're pushing into the couch, so that is an action, you're pushing into the couch, so then the couch pushes back up on you. That is the reaction. So it's always a pair. So an action reaction. So you push on the couch pushes back on you. The only one of those you draw in the free body diagram for yourself would be the couch pushing on you, because it's always on the object. That's why I have you write out that explanation after you draw the forces, to make sure you're only drawing the forces that are acting on that object. So the reaction is you push on the couch pushes back on you, and that's what we call the normal force. That's the perpendicular part of it that causes the object not to accelerate through. It's there just because the object is being supported. The other part of the interaction with the surface is the friction. So if I try and slide across, I'm pushing into the surface a little bit, and so there's a sliding force across, and so it resists that sliding force in any way. It's always in response to motion. It's always in the exact opposite direction of how the object is moving or sliding. So here's a simple case. You have a mass sitting on a table. It's at rest, so the net force is 0. When we look at the interactions, the earth is pulling down on it, so that's what we call the weight. And then the table is supporting it, we call that the normal force. And because it's not moving, Newton's first law says that if an object isn't accelerating, the net force has to be 0. So that means the upward normal force and the downward weight happen to be equal. They're not always equal, but in this case they are. If you have an incline, the normal force doesn't point straight up. We do have the weight pulling down, but the normal force is perpendicular to the surface. So if these are the only two forces acting on the system, what happens is the object will slide down the incline. There's no friction, there's nothing else, because those two forces can never cancel out, because they're not parallel to one another, and they're not necessarily going to be equal. So what happens is the weight, we actually look at what's most useful is kind of rotating our free body diagram so that our perpendicular to the incline and parallel to the incline are what we're actually looking at. And in this case, we look at the components of the weight parallel to the incline. So down the incline would be mg sine theta, and then perpendicular to the incline, which ends up being equal to our normal force in most cases, is mg cosine theta.